Hello, and welcome to another episode of our Climate 201 series on negative emissions technologies. This episode we're going to be talking about one intriguing idea that has been suggested in the past: enhanced weathering. Listeners to earlier episodes will remember that I had talked about the way in which negative emissions technologies can seek to perturb or change natural elements or processes in the carbon cycle. We discussed how there are very large natural flows of CO2 between different reservoirs in the Earth system, one of which is the atmosphere, where of course it absorbs outgoing infrared light, which has such a big impact on our climate. In the next few episodes we'll be talking about technologies that aim to change the rate at which carbon flows between these different natural reservoirs to achieve net negative emissions. First off is an idea called enhanced weathering. There are certain types of rock that, as they're exposed to the elements, they erode and so on, react with CO2 in the atmosphere. This process, where rocks are gradually broken down by exposure to wind, rain, acids, changes in temperature, plants that break them down, animals, rejection, criticism, disillusionment, psychic damage, as we all are. This process which breaks down rocks is called weathering. And this process of weathering rocks is in fact one of the things that regulates the amount of CO2 in the atmosphere on a long timescale, over many thousands of years, by gradually taking up excess carbon dioxide from the atmosphere and storing it in rocks. A lot of the carbon that gets taken up here is the weak carbonic acid, carbon dioxide dissolved in water, which can then erode away silicate rocks and react with them, forming bicarbonates and other forms of rock that store carbon more permanently. Often this bicarbonate gets washed into the oceans, sinks, and ends up in the deep ocean sink. So these rocks are breaking up, they're absorbing CO2, they're reacting with it, and they are being washed into the ocean and into the deep ocean sink, or the carbon is being locked up in the rocks through these chemical reactions of the weathered rocks. However, this process is far too slow to respond to the incredibly rapid addition of CO2 to the Earth's atmosphere that humans are undertaking at the moment. Natural rock weathering absorbs perhaps around 0.3% of our emissions every year by itself. This means that it tends to regulate climate naturally on timescales of hundreds or thousands of years, and of course the timescales we're concerned about here are years and decades. So the idea behind enhanced weathering is, could we speed up this process artificially so that it removes more CO2 from the atmosphere? Specifically, as with any chemical reaction, the amount of reaction that you're going to have going on is essentially proportional to the surface area available for the reaction. So the idea is going to be to massively increase the surface area of suitable rocks available to the air to take up CO2. And that's going to mean bullying some rocks, exposing them to criticism, breaking them down, that sort of thing. So one way you could do this is to mine suitable rocks from underground. Olivine is often mentioned as a suitable candidate material, we'll talk about it a bit more. Then you grind up that rock to a very fine size so that it has a much higher surface area that would be exposed. That will react with CO2, and you can sprinkle it over a very wide area of land. This might then do in a year what would normally take 1,000, and take up many tons of CO2 from the atmosphere. One advantage, of course, is that this all occurs by natural chemical reactions and weathering, and therefore you don't need to do any explicit storage element here, because you've just formed new rocks and they will probably end up in the deep oceans or being washed away anyway. So let's dig into this in a little more detail. First of all, it's not going to surprise you to hear me say that in this, like in everything else related to negative emissions, the Hornies Law applies. That is to say, if you want to try and use negative emissions to suck in CO2 emissions to compensate for CO2 emissions, your activity needs to be on a similar scale to the industry that's currently putting CO2 into the atmosphere, which happens to be a pretty big industry. And it should be quite clear that if you want to remove billions of tons of CO2 from the atmosphere, which is the sort of scale we're talking about to have a big dent on our climate emissions at the moment, you're going to need billions of tons of ground up rock to do it. It's not like a single molecule of rock can absorb hundreds of molecules of CO2, after all, in these fundamental chemical reactions. In terms of the basic chemistry for olivine, for example, the theoretical maximum efficiency is that 1 ton of olivine will absorb 1.25 tons of CO2. In reality, this is of course a theoretical maximum, we would expect it to be less than that in practice. So, for the sake of argument, let's just say that it's 1 tonne of olivine gives you 1 tonne of CO2. So, you'll need billions of tonnes of rock to absorb billions of tonnes of CO2. So, to give you an idea of the sheer scale here, one study suggested that you could add around 20 tonnes of ground up rock per hectare per year to 2/3 of the world's productive cropland. That's a pretty big area, 2/3 of all of the crops that are being grown in the world. That's a large area under cultivation. If you did this, that would take up between 0.5 and 4 billion tonnes of CO2 out of the atmosphere per year by 2100, which is somewhere between 1 to 10% of our current global CO2 emissions. And, at the upper end there, 4 billion tonnes of CO2, that would be a really big fraction of the negative emissions that are appearing in models. Another older scientific paper, Kohler et al. 2010 for the nerds, suggests that if you spread crushed olivine for enhanced weathering, it could absorb around 10% of our current annual CO2 emissions every year. But to achieve what they do in Kohler et al., the land area you have to spread it across is just the tropics. All land between 30 north and 30 south, which is obviously a pretty vast swath of territory. So when I say at scale, I mean you have to sprinkle billions of tonnes of ground up rock across hundreds of millions of hectares every year to achieve an effect on this scale. And if you think this is a lot of effort to go to just to cancel out somewhere between 4 days and 6 weeks of our current CO2 emissions in a year, then you might reflect on how much more urgent it is to start cutting CO2 emissions dramatically now with investment in deploying clean tech and reducing our wasteful consumption. But nevertheless, if we are going to end up in a scenario with large-scale negative emissions on the order of billions of tonnes, then we can't afford to leave any solution unexamined that has the potential, at least, to remove billions of tonnes. The reason why we talk about putting this on managed cropland is multiple, really. First, of course, we know that the infrastructure actually exists to relatively easily sprinkle the rocks there. They're regularly ploughed, managed by individual landowners and so on. Stick this ground up rock in the tractor and perhaps that'll be a good way to start. Secondly, lots of these chemical processes work better when the rocks can get wet, so somewhere with rainfall where you're growing crops already is likely to be helpful in this. Thirdly, some have argued that adding rocks to the soil can, depending on the soil and the type of rocks involved, help to lock in extra nutrient levels, maybe reverse some of the acid rain and acidification of the soils by reacting with that carbonic acid from acid rain. That would perhaps help to reduce our dependence on fertiliser somewhat. And of course, a big part of our nitrogen dioxide emissions comes from this nitrogen fertiliser, which we're all using to have the bumper crops that we rely on today. In the case of rocks that have calcium and magnesium in them, certain plants need these to grow, so this might help promote their growth where it's limited by these nutrients. It may also result in decreased erosion in some topsoils, because you have this extra material that can wash away, which can in turn help the soils stay together and reduce some of the sea level rise that is caused by that erosion of soils into the sea. Another possible co-benefit that might arise shows up because of the alkalinity of the rocks as it spreads into the rest of the climate system and the Earth system. Our CO2 emissions don't just warm the climate. The CO2 absorbed by the ocean causes the oceans to gradually become more acidic. They become very weak carbonic acid, which is in turn contributing serious damage to marine life, coral reefs and so on. Adding this alkaline sprinkling of rock will probably serve to counteract that somewhat, although again you would expect the effect to be on a similar scale to the effect you'd have on CO2 emissions, so it's not going to reverse ocean acidification all by itself, but as a side benefit it would probably help to slow it down. One more argument from this from advocates is that you can co-locate it with other forms of negative emissions as well, potentially. For example, sprinkling enhanced weathering rocks on crops that will also become biofuels that will be used for BECCS in the future. One more argument for this technique from advocates is that you can co-locate it with other forms of negative emissions as well, potentially. So, for example, in your maximal negative emissions ecosystem, you can imagine sprinkling these enhanced weathering rocks on crops that will also become biofuels that will be used for BECCS in the future. And perhaps those crops are alongside some afforestation as well, or maybe you're using them alongside biochar or careful soil management when you're growing these crops as a way of sequestering more CO2. As I'm sure you can appreciate by now, many of the key ways that we would seek to get negative emissions to function, particularly when they involve enhancing the land sink like this, involve our ability to cultivate and manage a huge amount of land in various different ways that have carbon in mind. If we had farmers and land managers who saw their jobs as contributing to this effort, or who were incentivised to do this at scale, then we might expect enhanced weathering as part of a big portfolio of different things that would enhance the land sink overall on managed land. Indeed, the first part of any effort to get here would obviously involve ending all of the destructive practices in agriculture and forestry that currently add to the climate burden of our activities, but that's before you get to the negative emissions stage. So these are some of the advantages of enhanced weathering as a solution. Now let's talk about some of the limitations for doing this as well. The first and most obvious one is that you actually have to crush up these rocks into a very fine powder. Perhaps that powder would be a few microns long, each grain, and doing that requires a good deal of energy. To give you an idea, you might need 1.5 gigajoules per tonne of rock. If you're going to operate those grinders that are grinding up that rock, you will probably need to burn fossil fuels to do that, or find some very efficient electric grinders and power them renewably. If you're grinding up billions of tonnes of rock every year to do this, it becomes quite a high requirement for energy by the end of it. So as you can probably see, there are some of the same concerns with enhanced weathering as there are with biofuels for BECCS. In that episode we talked about the requirement to act over vast areas of land. We also talked about the concern that you need a whole life cycle assessment. So yes, the ground up rocks will absorb CO2, but what about the extra energy that's expended in grinding them up, the CO2 that might be emitted by vehicles that spread them, the CO2 that's emitted in the mining and transportation operations for the rocks, and so on. Key point here, of course, is that the net impact of your activity as a whole, doing it versus doing nothing, has to be taken into account here. Generally, all of these impacts tend to reduce the practical effectiveness of your negative emissions technology significantly below the technical potential that you would calculate for it, the headline figure that you would get, assuming that everything works perfectly or not taking these things into account. For example, there was one study which suggested that the energy expenditures in grinding and transport would reduce the efficacy of using olivine for enhanced weathering by around 10 to 30%, so it's 10 to 30% less effective at sucking up CO2. But of course, this depends on a whole bunch of assumptions that are made about how this will work, and it may not end up being deployed in the most carbon efficient way, like other negative emissions technologies may not. In very bad cases, as with the bioethanol example I like to use, the effect can end up being quite minimal, and there's a concern that once you actually measure the effect, it will probably be smaller than what you can calculate. Another point that you need to consider with enhanced weathering is that there's a great deal of potential variation in how effective your finely ground rocks will be at absorbing CO2, how long term it will stay there, and all that stuff is going to depend on a number of different factors. The chemical reactions that are going to take place with this rock will depend on a number of different factors. The purity of the rock will matter, so will the location that you're spreading it, so will the amount that the rocks can be disturbed. It's actually better if they're regularly churned about by natural motions or the motions of agriculture. The moisture, atmospheric conditions and so on that you don't really have much impact over, all of these things will change the efficacy of the chemical reactions that can take place. There are important aspects of the chemistry to consider, such as unwanted chemical reactions which can reduce how much carbon is being taken up here, and different agents have been suggested to use to bind the carbon, and different rocks have also been suggested. So the effects that you have is very contingent on all of these choices. And unfortunately, with many of these studies, what we really have to rely on is a lot of observational studies that are done in small patches. So there was even a study in Ireland where this was done, I believe, on a few fields, say, where they try and figure out what they can do, and then they try and extrapolate them to the entire world when they make these estimates. But clearly that's a very difficult thing to do, which is why the estimates for how effective enhanced weathering would be can vary so much. As we mentioned, between 0.5 and 4 billion tonnes of CO2 as a possible range for applying olivine across 2/3 of agricultural land. Clearly this is an area where a great deal more research is genuinely needed, because it feels like the difference between 0.5 and 4 billion tonnes a year could easily be the difference between deciding that it is worth attempting at scale or simply too much hassle. And of course, when you convert this into dollars and cents, it's difficult to undertake a project when you have a sort of factor of 10 uncertainty about how effective that project is going to be at achieving what you want. There are some other concerns to consider here. One, of course, is the environmental impact of the mining itself. Thinking specifically about olivine here, as it's the most studied material, we're talking about around a 1-to-1 ratio of tons of CO2 and tons of olivine that would be needed. To get right up to the end of these projections, where we might sequester olivine, 10% of our annual emissions with olivine, we'd need 4 billion tonnes or so of olivine then to get 4 billion tonnes of CO2 pulled out of the atmosphere. In 2019, 8 billion tonnes of coal were mined. So to say this is on a scale similar to the fossil fuel industry in reverse is once again exactly right. Indeed, if you were doing this, I think olivine would end up being perhaps the second or third most mined material in the world. Now, there's no shortage of olivine. It makes up a huge proportion of the upper mantle of the Earth and is common in the Earth's subsurface, so it does seem like there's the potential to expand our production pretty substantially. But you would have to scale it up pretty substantially. Currently, olivine is produced on the order of a few hundred tonnes a year, used for a few niche industrial purposes, and for this to work at the scale that we're imagining here, it would need to be in the billions for this to work. So before you start buying up olivine plots and trading in olivine futures, let's talk a little bit more about some of this. There are, of course, concerns about some of the potential side effects as well. In places where acidification is a problem, this technique could potentially reverse it. In fact, mitigating the acidification of soils alongside adding in these nutrients, calcium, potassium and so on, that's part of the co-benefit that might happen here. But there is also a concern that you might go overboard and shift systems into a more alkaline regime, and maybe that could have detrimental impacts on ecosystems that aren't used to it. All of the crushed rock ultimately ends up in the ocean via rivers and other marine ecosystems, so any impact that this has on the hydrological cycle, and creatures that live in freshwater, would need to be investigated thoroughly before you'd be happy about dumping all of this rock on this scale, in much the same way as we need to investigate the impact of our fertilisers and so on ecosystems. I would potentially be concerned as well about the human health impacts of some of the fine particle sizes that could potentially be used here. We know that air pollution is a huge contributor to premature deaths, and if this contributes in any way to fine particulate matter or dust that helps to cause these problems, that would obviously need to be seriously assessed as well. So in this case at least, there's an argument for more field studies to be undertaken to narrow down some of these unknowns that we can't quite determine for ourselves yet. Of course, and again relevant as you start to trade in your olivine futures and get your big mining machines out to get this wonder rock that will soon be the second most mined substance in the world, there is one more metric that everyone likes to talk about, which is the cost. There was a review of this academic paper called Streffler et al. In 2018. That was called, helpfully for once, Potential and Costs of Enhanced Weathering. This suggested that enhanced weathering could remove CO2 at various different costs. Perhaps $60 a tonne of CO2 removed for a rock called dunite, which is a type of olivine. An article from our friends at Carbon Brief put cost estimates at a range between $52 and $480 per tonne of CO2 removed, depending on a variety of different factors. You will remember from previous episodes that a widely quoted good price for removing a tonne of CO2 from the atmosphere is around $50. So at the lower end of these estimates, we're coming close to competing with other methods and getting cost competitive with some of the things that people have considered as a price on carbon. For example, that's about the same price as a tonne of carbon capture and storage, and slightly more than some of the cost estimates for BECCS. Now there is another technology that I want to briefly mention here, which is quite similar, which is similar in operation to enhanced weathering, but focuses on the oceans and enhancing the ocean sink instead. This is sometimes called ocean liming. By the way, both large-scale enhanced weathering and ocean liming are sometimes referred to as a type of geoengineering scheme. The technical definition of geoengineering is just large-scale intentional intervention in the Earth system to counteract the effects of climate change. I can certainly see why you would say that sprinkling rocks over most of the Earth's surface meets that definition. It is trying to do some large-scale engineering here, intervention in the Earth system that would counteract the effects of climate change. Now, my personal preference is just to use geoengineering to mean methods that attempt to reflect sunlight back into space, which are fundamentally different for a number of reasons. But maybe the real definition of geoengineering should just be, I can solve this problem by dumping a vast amount of X into Y. And next week we will talk about other types of X that you might want to dump into Y, where Y is the ocean. In the case of ocean liming, though, the idea is essentially to crush the rocks as before. Hopefully you're getting your energy from renewable sources again, so that the whole thing is carbon neutral or carbon negative, and then you dump them into the ocean instead. For example, you could include them in the tracks of ships for ships that are already sailing as something that they release intentionally, or you could put them in the shallow ocean close to the surface layer, which would allow them to mix. Then the same sort of chemical reactions take place, absorbing CO2 from the oceans and the atmosphere, countering ocean acidification as in enhanced weathering. It's been suggested that you could do this with lime or calcium oxide from limestone. The problem there is that limestone is calcium carbonate, and so producing lime from the limestone releases CO2. Basically, you've got calcium oxide and calcium carbonate, right? And the reaction is calcium carbonate goes to calcium oxide and CO2, and then you're sort of trying to do that in reverse, and you'd be producing... you'd be getting limestone back again that would sink to the bottom of the ocean, that would absorb the CO2. So really, this type of ocean liming is not that great on its own. The only way it could provide negative emissions is if you had CCS when you're producing lime from the limestone. So you'd get limestone, you'd make lime, you'd capture that CO2, you'd bury it, and then you'd spread the lime on the oceans, and that would absorb CO2. Now that's possible then. Effectively, the net impact of all of this, once you've taken out the cycle elements of it, the life cycle assessment elements of it and the side effects of it, would be converting diffuse sources of CO2, like planes and cars, into a point source at the location where you're producing the lime from the limestone. Does that make sense? So you have like a plane in a car that's emitting CO2 willy-nilly into the atmosphere, and then you are sucking that in with the limestone, with the lime, and of course that is a net neutral process because of the way that you've hopefully produced the lime. So it does kind of allow you to do CCS on distributed emissions with these extra steps. And in some ways it's not that dissimilar to what direct air capture does, which is a sort of CCS that relies on these similar chemical reactions, but not always using lime. I mean, yeah, people have talked about this. The cost is expected to be somewhat similar. I mean, it's not entirely useless, I suppose, because, of course, you can more easily capture and bury CO2 from a point source, a big factory where you're making lime, as opposed to individual cars and planes all over the world. But it does seem like a pretty expensive and elaborate way of going about negative emissions, and, of course, you need to deploy CCS as well, which we've already talked about. So I won't really elaborate on that idea further, aside from mentioning it, except to say that people have also proposed sprinkling rocks in the ocean, and the process is quite similar to the process of sprinkling them on land. If you would like to read more about this, a guy called Phil Renforth has published a number of in-depth studies into it, but for now I'll probably just leave it at that. So in the end, what can we say about enhanced weathering? On this one, I don't really know whether this scheme is particularly likely to take off. If the agricultural benefits are genuinely good and worth having, it may be that this sort of tips it over the edge into something that people do. Really, thinking about it as an idea just sort of emphasises to me how huge negative emissions schemes have to be really important to actually get to the levels that we're imagining that they might be in some of these models, you know. We're talking about to get 4 billion tonnes, 4 gigatons of CO2 of negative emissions, which is, you know, not uncommon as an amount of negative emissions that you see in these climate system models, you know, in these IAMs. You need the entire tropical zone, 30 north to 30 south of land, needs to be covered by crushed up rocks that you're going to get from somewhere. I mean, that's a heroic effort. You also need to set up a mining operation for olivine to do this that is on a truly monumental scale. Compared to today, it would become one of the most mined minerals in the world. I think I worked out it would be second only to coal today. You'd be mining more olivine than iron ore to get this 4 gigatons of CO2 removal from olivine. But on the other hand, looking at it in this way, okay, so maybe it won't provide 4 gigatons of CO2, but it could provide a few 100 million tons. It could provide less than that. And one of the advantages that it does have is that you can deploy it alongside other solutions as well. It might not compete for land in the same way that, say, afforestation might compete with BECCS. It will compete for energy, and the mining operations may compete for water, so you have to take that into account. You're obviously trying to do all of this within boundaries, and there will be certain places where the technologies make sense to deploy and certain places where other technologies make sense to deploy and all that sort of thing. But I think that co-benefit does make you consider it and continue to consider it. I have to say that in light of everything, I would be surprised if a massive enhanced weathering operation on the scale that we've sort of imagined and described here is ever going to exist. But it would be interesting if at some point an active market for carbon credits, where farmers go out of their way to purchase, will incentivise them to use something like olivine for its co-benefits and its carbon benefits. And you could have a lot of managed agriculture where this is happening, a bit like biochar might happen, a bit like soil carbon sequestration might happen. And eventually something like this could contribute a little to mopping up some of the residual emissions from a largely decarbonised energy system. And pretty much everyone agrees that it's obvious that any real negative emissions scheme will use aspects from each of the technologies evolved where they make sense. So, if you can get 5% from afforestation, 5% from enhanced weathering, 5% from BECCS, 5% from DAC and so on, it does start to add up to something substantial when everything is done in concert, if these different processes don't interfere too much with demands for water, land, etc. So, like many of the technologies we've discussed, it's intriguing, it's scientifically interesting, there are advantages and disadvantages to consider. It would need to be done at a pretty mind-bending scale, and it's not being done at the moment, to cancel out a decent fraction of today's emissions, so we still need to decarbonise rapidly, and we certainly can't rely on this materialising to save us from climate change. And possibly in the future, if the incentive structures exist to remove CO2 from the atmosphere and people are actually willing to pay for it, this might be one of the things they do to remove CO2 from the atmosphere and get accredited for doing it. And it would be good to see some more research that will narrow down some of these uncertainties in how effective it will be. And then it might occur particularly in places where it's especially economical to do so. And that, my friends, is all I have to say about grinding up little rock friends to absorb CO2 and the process of enhanced weathering. Thank you very much for listening to this episode of Physical Attraction on negative emissions technologies. You can find us on the web at physicspodcast.com. There you will find the contact form. You can get in touch with us with any comments, questions or concerns you have about the show. You'll find the episode guide, a list of all the episodes we've done and all the topics we've covered over the years, the people we've interviewed, descriptions of them. Send it to your friends, send it to your enemies, send it to your podcast fans, tweet about it, put it on letters and post them up around the town, shove them through people's letterboxes, talk to people on the street, wear t-shirts, branded t-shirts that advertise this to people. Let them know that there is some amazing podcast content out there that they have not found because it doesn't show up in their podcast search engines and because it's not by Hillary Clinton or Bruce Springsteen or Barack Obama or any of the many, many famous people who have decided to start hosting podcasts. I would really appreciate it if you did that. There are, of course, other ways you can support the show beyond getting in touch with us. We're there on Twitter, PhysicsPod. You can find the subreddit, Physics Podcast. If you want to go and chat about some episodes there, feel free to do so with fellow fans. You can support us on the Patreon. If you're listening to this early, you are hearing it on the Patreon. Welcome to the Patreon, and thank you for your support. I appreciate it. You can find many of our early release episodes there, and special bonus episodes only available to those who help support the show. I deeply, deeply appreciate all of those of you who have done that. Thank you for helping me to keep this going, to pay the hosting costs, to buy coffee for myself, which I obviously need a bit more of today, and the various things that I have to convert into these episodes for you. I do appreciate all of your support and help. What else is there to say? Enjoy your lives. Until next time then, please do. Take care.